Hi everyone, welcome back to our discussion of chemical reactions, balanced equations, and performing calculations. And in this part we're going to look at the calculations based on the stoichiometry, the actual reaction, and how these compounds are reacting in molar ratios. So balanced chemical equations are how we look at what is going on. We can put it down on paper so we can theorize what we're going to see when we get into the lab or into the real world, like a plant, whatever we're going to be doing. So it's important that we can do that, because that will help us plan things and decide, okay, how long is it going to take? What materials do we need? What are we going to use up? And so what kind of waste are we going to produce? I mean, there's all kinds of really important things that we get from this. So the coefficients in the chemical reaction tell us the relative amounts in moles of each substance that we're doing. So if we have 2 COs, that's a gas, that means it's 2 moles of CO plus 1 mole of O2 is going to give us 2 moles of CO2, and so we would need to plan for that. If we are going to be producing CO2, that's what we're trying to do in this case, and so we need to be sure that we have whatever's on hand to scrub that or capture it however we need to. So 2 moles of CO is equivalent to 2 moles of CO2. So another way of saying that is, for every 2 moles of CO, we're going to produce 2 moles of CO2, but it's only going to take 1 mole of oxygen. So the 2 moles of CO is equivalent to the CO2 in this case. So since remember that conversion factors are equivalent, so that means that we can have 2 moles of CO over 2 moles of CO2, or we can even reduce that, 1 mole of CO to 1 mole of CO2. And remember, we can always flip that, and depending on what we need to cancel out in our units. And so in this case, we may be actually doing compounds that we need to cancel instead of just numbers and units. So I know this is kind of a busy slide, but in this, what we're trying to show you is how we would use that conversion, because it is allows us to decide the stoichiometric amount of each component that we're going to do. So if we have 3.82 moles of CO, okay, then that means that since they're on a 1-to-1 ratio, 2 to 2 or 1 to 1, right? That means that we're going to produce 3.82 moles of CO2. Now, going along with that, though, if we have 3.82 moles of CO, it is only going to take 1 mole of O2 for every 2 moles of CO, so I only need 1.91 moles of oxygen. So that's the only way that we can get from one thing to the other, because remember our molehill, we can't go directly from grams to grams. That would be going under the molehill. So we have to go over the molehill, and what I mean by that is that we can start with moles or grams of one thing, but we're going to have to change from one mole type to the other mole type at the top of that hill in order to calculate the grams or the number of particles of that when we get done. Okay, so for me, I don't know about you, but it's a lot easier for me to look at something. So I'm going to work it, and I think it'll make more sense. Okay, so I just put little pictures of my molehill up there so that'll kind of remind us. So calculate the amount of urea, okay, in grams, and so this is the urea right here, in grams that will be produced by the complete reaction of 5.25 moles of ammonia. So I'm starting out with 5.25 moles of ammonia, which is NH3. And I'm in moles. I'm just wanting to know how many moles of urea I'm going to make. And then once I get to moles of urea, I can always get to grams of urea. Okay, so I know that I need to get rid of moles of ammonia. And I'm wanting to get to urea. Eventually, I want grams of urea. I'm just going to write urea because the formula is really long. So when I look at my balanced chemical equation, for every 2 moles of ammonia, I'm going to produce 1 mole of urea. So 2 moles of ammonia is going to react with 1 mole of urea, which is NH2, 2, CO. See, told you it was long. All right, so what that does is it gets me from moles of ammonia to moles of urea. And then it's wanting me to know how many grams of urea is going to be produced. And if you count that up, 14 times 2 is 28, plus 4, plus 12, plus 16. That's going to come up to approximately 60 grams of urea for every 1 mole of urea. It takes a long time to write this with this little pen. Okay, so that gets rid of moles of urea, and then that's going to leave us with grams of urea, which is what we want. Okay, and so when we do that calculation, 5.25 times 60 equals, and then divided by 2, and that is going to give us 2.63 moles of urea. And then when I multiply it times the 60 grams, that tells me that I'm going to need 158 grams of urea, right? So I did that all in one long step. So I'm just telling you, I got the 2.63 moles, but then I had to multiply it by 60, right? And then that is where I got the 158 grams. Okay, let's do another one. All right, so determine the stoichiometric amount of carbon dioxide required to react with the 5.25 moles of ammonia. So I can do any of these things that are involved in this reaction. It doesn't matter. I can do the product, I can do something else, I can do the water, I could, any of it. But so I still have the 5.25 moles of ammonia. But this time, there's 2 moles of ammonia because it's still in that same balanced chemical equation. But it's asking me how much carbon dioxide. Well, there's 1 mole of carbon dioxide for every 2 moles of ammonia. All right, and so then it wants to know what is the amount of CO2. And so again, that it's 2.63 moles of CO2, right? But this time, a mole of CO2 is 44 grams. And so that's going to tell me that I need 116 grams of CO2. Okay, so some people they would calculate the moles and then they'd multiply it by 44 or whatever. But it's really nice, especially as we get into more complex reactions. I don't know what I did. I went all the way back to the beginning, I think. So no matter what I did, I would be able to know how much I'm going to need of everything. Okay, does that make sense? I hope. Sorry about this like crazy little journey here that I took. So we did a stoichiometric ratio. If I can get back, I promise I can get back. I don't know why it's doing this to me. Stop. Okay. All right. So 116 grams of CO2 is the bottom line. Okay. So that's what it would take of CO2 for me to do this reaction if I had 5.25 moles of ammonia. So that gives us this molar ratio of how we're going from one thing to the other. But most of the time, we're going to get grams of something because we don't measure moles in the lab, we measure grams in the lab. And so this is where we're going to do the grams to moles, moles to grams thing that you may have heard of in other classes, okay? Because we have to be able to go from grams of one thing to grams of something else, and in order to do that, we're going to have to use this molar ratio, okay, which is what's up here at the top of my little molehill, okay? And so that's all we were doing. So we went from moles of one thing to moles of something else, and then we took the moles from that something else to grams. So now we're going to take it all the way from grams of something to grams of something else. And I've got this little X down here to remind you that you can't go directly from grams to grams, from grams of one thing to another. You have to go over the molehill. You can't go under. Okay? Hope that makes sense. All right. So in this example, we have nitrous oxide. And nitrous oxide is the gas that they give you in the dentist's office. Sometimes it makes you feel like you're kind of floating. It's made by heating ammonium nitrate, okay, and then it produces the nitrous oxide plus water. And so this is the balanced chemical equation for you. When you see an equation, always check. Usually if it's got numbers, if it's got coefficients, it's probably balanced. But if you don't see any, always check. It's always a good idea to check and make sure that it's balanced. Okay? All right. So in this particular reaction, we're going to start with 10 grams of nitrous oxide. So we're going to produce 10 grams of nitrous oxide, and so it wants to know how much ammonium nitrate, okay, that we're going to have to use to do that. So we start with our 10 grams, so 10.0 grams of nitrous oxide, and the first thing I know I've got to do is I've got to convert that to moles. So the formula weight of N2O, and again I've done these ahead of time, but it's nitrogen times 2, which is 28, and oxygen times 1, which is 16, so that's 44. So there are 44, and you've got to go down below because you're going to have to get rid of grams of nitrous oxide. So in 1 mole of, sorry, it's N2O, not NO2. That's going to get me to moles of nitrous oxide. Then to get from moles of nitrous oxide to moles of ammonium nitrate, I've got to use that molar ratio from the balanced chemical equation. Now in this case, it's 1 to 1. I still write it so I remember what I'm doing, okay? So 1 mole of nitrous oxide reacts with 1 mole of ammonium nitrate. All right, so that gets me from that got me from grams of nitrous oxide to moles of nitrous oxide, and now I'm to moles of ammonium nitrate. But it doesn't want moles of ammonium nitrate, it wants grams. And so what do I have to do to get to grams of ammonium nitrate? I'm going to have to do the molar mass of that. And so the molecular weight or molar mass of ammonium nitrate, I went ahead and calculated it for us earlier, is 80 grams. And again, you know how to do that. In 1 mole. I'm trying to write little so it'll all fit on this line. So, all right, it makes me even messier than normal. All right, and so then 1 mole of ammonium nitrate. I'm now to grams of ammonium nitrate. And again, if you're not a calculator genius, make sure that you multiply everything on the top and press enter, and then multiply by everything on the bottom. Put that in parentheses if you want to be sure. But this is a great time, remember, when I'm doing these sample problems, for you to check and make sure that you're doing your calculator correctly. And so I got 18.2 grams of ammonium nitrate. Okay, so determine the corresponding mass of water produced in the reaction. And so it starts out the same exact way, except in the case of water, remember, you've got to go back to this. That's why I always do it. 10 grams of N2O. Convert that to moles. And if you already know what your mole number is, you can just start with that, I guess. 44 grams of N2O. Now this time you've got to remember to do that molar ratio. So it's 1 mole of N2O to 2 moles of water. And again, that's why I always do this. Even if it's 1-to-1, I still do it because it reminds me of where I'm going. All right. And so then I know that in 1 mole of water, I just remember this one, it's 16 plus 2, is 18 grams of water. And so as far as the water is concerned, it's going to produce 8.18 grams of water. Big thing, don't forget your molar ratio. That's very, very important in these stoichiometry problems, because if you forget that, then you're going to be, your answer's going to be wrong. Okay, so there's your practice problem. And then when we come together next, we're going to look at something called limiting reactants.